I'll take 1 second.
Yep.
Okay, I will be returning your quizzes today. I just want to make a general note. I think some of you answered the second question on the second page, similar to the question of the quiz example that I put online, which was the wrong answer. So it was ion exchange is the wrong answer. Some of you did put ion exchange and put the gradient illusion similar to ion exchange illusion, and similar to the answer of the sample quiz online. So what I want to point out is, as I put sample quizzes online for you, this is to give you an idea of what the quiz will be like or the test will be like, but definitely not the same question. So I won't ask the same question. So I just want you to see the level of detail I would expect in a quiz and how the format of the questions are. So just take note of that, because I think few of you just answered the question same as the example quiz. Okay. With that, I'll let Gary take over.
Joy? I don't know if this is in the way of anybody or not, but we'll get rid of it anyway. Well, good. So back to gas chromatography. Really, first lecture, we do spend 2 lectures on this, and normally it's a 3-day course. It's like everything else, it seems, let's all condense it and put it into one fairly small time slot. So tried to pick highlights. But we spent some time introducing just the topic, talking about hardware. And that's kind of where we ended, talking about hardware. What physical parts of this equipment make it work? What do they do? And we were talking about detectors at this point. And our last one is really mass spectrometry. And so this is probably one of our most important detectors when it comes right down to it. Flame ionization is the most common. And then we've actually moved to mass spectrometry. Back in the days when they introduced this combination, it was extremely expensive, and people couldn't afford it. Now it's reasonably cheap. It's probably somewhere around $140,000, $150,000 to get a setup that works. That's quite different from what it was when it started, believe me. And so we see a lot more mass spectrometry today than ever before. This mass spectrometry does a lot of things for us. One of the most useful things, it's a very specific detector. This is a chromatogram, which you probably can't see very well. There's a little segment in here of some kind of small peaks, and that's blown up, so you can actually see what they look like up here. And what the mass spectrometer is doing is it's just sampling ions in the mass spectrometer over time. And so it just looks at total number of ions. It doesn't tell you how many compounds they're coming from. It doesn't tell you what the compounds are. It just simply says, oh, something's coming through at this point. And based on the area, it's about some rough measurement of how much is coming through. So this area is expanded. And so what it's drawing for you is it's drawing this orange line. And if you look at that, you might say, oh, here's a peak. Here's another peak. OK, here's another compound. If you start looking truly at what those peaks are made up of, it's really quite a different story. This peak right here is primarily made up of one compound. And then, but we get to this one, and this orange one you see, that's the sum of this compound, the sum of that compound, and the sum of this compound. 3 individual compounds make up what appears to be one peak. If you were doing this by any other detector, you wouldn't know that. You'd just get a trace and you'd say, must be the same thing. It must be all pure. It must be one compound. Mass spectrometry starts, or does, actually give you the ability to look at that peak and say, what is it and how many things are there? When somebody shows me a peak on a chromatogram and they say, look, this nice peak I got, it's beautiful, this is what it is, I look at them and say, how do you know? Really, how do you know? You don't. By normal LC detectors, by normal GC detectors, you know something's there, but you don't know what it is until you get a mass spectrum of it. And so basically, each of these peaks you can see are made up of different compounds. And this is this last one here, kind of blown up a little bit. It seems to have left off this peak down here. But this is actually a mixture of at least 3 different compounds. And it's compound 37 and 38 when we start looking at identifications. So we can, the way mass spectrometry works, and we'll spend time with that, what happens when a compound elutes from the gas chromatograph, it's hit by high energy electrons. Those compounds are blown into bits and pieces, and then the machine counts the pieces. It's like a jigsaw puzzle, right? So you got a set of pieces that it measures, and those pieces are unique to a given chemical. So what it's doing is looking at blowing a compound or blowing whatever's in that peak area apart and looking at the parts that you get. And so by putting those pieces together, you say, oh, this is this compound. Oh, this other is this compound. So like I say, it gives you an ability to know what's there. And actually then I can set the mass spectrometer up to just measure the bits and pieces for this compound, and it will measure nothing else. So there can be peaks, there can be compounds all over. If I set my mass spectrometer to look for these puzzle pieces, I can avoid everything else in nature. So it's an extremely powerful tool, a very, very sensitive tool. So it's something, like I say, we really need, and we make a great deal of use of these days. So moving off detectors, off hardware, then talking about how do we get better separation, how do we do a good job in chromatography. And so we tend to work with 3 different parameters. Now, when you talk about the theory of chromatography in general, you probably have seen this equation. The first term of this equation, this is resolution. I want high resolution. I want to maximize that number, my separating ability. So 1 is the selectivity of my column. Does my column really have an affinity for some components, no affinity the others, so they get separated very nicely by the way they interact with the column? The second one is more of what we call a capacity term, which isn't really a good term. It just measures kind of the total idea of, is there an interaction and when does the interaction occur? The last one we spend a lot of time with, a lot of worry over, and this is what we call theoretical plates. And so we'll kind of go through each of these a little bit so you get an idea what we're taking advantage of to get our separation. And we'll be using certain terms when we do this discussion. This is the idea of column efficiency. This gets us in the category of how well peaks stay together, how sharp those peaks are. You know, if I got a compound and it elutes over that area, that's not very good separation. It's hard to separate one thing from another. If I've got a peak like this, it's easy to separate them and measure each of them individually. So with this particular type of term, or this term, column efficiency, we want a high number on column efficiency. The higher, the better. The sharper the peaks are. They can come anywhere and be nice and sharp, easy to separate from each other when we have a high number. As this number goes down and down and down, our peaks are getting broader and broader. It's hard to separate one from another. They're overlapping. And so we really like to work at higher efficiencies. So that would be out here. The problem is this comes largely through the size of the column that we're using. If the big fat column, your airflow isn't very uniform, things get mixed up, things get to be pretty poor in terms of separation. But tiny, tiny column, then we tend to get more uniform flow through that column, gas flow. And so small columns, nice flow properties, high efficiency, large columns, very poor efficiency. So we might say, do we want to always use small columns? Not really, because if we get out in this region, these columns are so darn small, I can't put much on them. I can't get much detection. So it's a trade-off. And so what we tend to work with, we tend to work more in this category, this 0.2, 0.25. Still quite efficient. But again, they're big enough that I can actually put some material on, enough for detection. We stay away from anything out in this category if at all possible. Our separations tend to be very, very poor. This one that I always like, I like this figure particularly because it goes kind of counter to past history. I think it's always fun when things turn out to be different or you don't get the same answer you expected. And so this is kind of one of those types of examples. Our mobile phase, I said it's a gas, right? And what can these gases be? I mentioned helium and hydrogen as the two preferred gases. It'd be a lot cheaper if we'd use actually nitrogen. That would really be ideal from a cost standpoint. But I want to explain this figure. And we have a different metric over here. This isn't the same as this one. Notice we got 3,000, 9,000. We're dealing with a different term. This term we want to be minimum. So the smaller the better when we look at efficiency this way. So we really, what's our lowest, what's our best efficiency? Gives us the lowest number? Nitrogen. And we don't use it. Why don't we use it? Mainly because we get that wonderful efficiency when the gas is flowing through the column about 10 centimeters per second. Very, very slow mobile phase movement. If it moves very slowly, you don't get many results. And so we could really get some nice efficiency, but it takes us forever. Time is money. We're always looking for how do we get the most data in the least amount of time. So this really looks inviting. But look what happens. So we start moving, let's double our mobile phase speed. That cuts our analysis time in half. So this takes me half of the amount of time to get my separation. At that point, oh, we're not looking so good. Our other gases are better. If I want to really push it out here a little bit more and say 40 mils per minute, which is, or 40, I'm sorry, centimeters per second, that's velocity, we're way up here. Our column is useless to us. So what do? We go with either helium or hydrogen. You look at this, really fast flow rates. I can get this analysis done in 1/8 of the time, 1/10 of the time by using these gases as that one. And yes, we suffer a little bit as we go to faster flow rates, but not so much. And hydrogen is actually the most efficient. So if we use hydrogen as a carrier gas, it's most efficient. We go the highest velocity, have the shortest analysis time, and the best separation.
So it looks like generally speaking, like the heavier the gas is, the less efficient it is when you have like a higher flow rate. Is that just due to like atom size, or is there some other?
Why is your question? It deals with viscosity of the gas primarily. These are very, very low viscosity gases. And so their flow properties in that column is quite different than a high viscosity gas. And so that's the major factor that goes into that. So what do? We recommend hydrogen. That is the primary gas by far from a cost, from a performance standpoint. Is it going to blow up? As I said, no, it's not going to blow up. You really have to work at that to get anything going wrong with that. So what do we use? We use small columns. We use hydrogen as a carrier gas for us. And I said there's a coating on the inside of that column. We're actually chemically bonding a thin film inside of this glass column. And that's our phase, our stationary phase. And we got a choice there too. Do we want a thick coating or do we want a thin coating of that stationary phase? And so a thick phase means I can inject bigger samples. I can have more material going into my column that potentially can help me in detection limits. If I go with a thin phase, I can't put as much on that column, and that can hurt us a little bit in sensitivity. But this gives us much more resolution. And so we like to go with a thin phase. Small volume, hydrogen is a carrier gas, and a thin coating inside of that column. That gives us our best separations. Column length. Longer means better separations. You know, that's very typical. You've got 5-meter column, 10-meter column gives you better separation. 20-meter column gives you better separation. The problem is, if you double your column length, your separation only improves by 1.414, the square root of the length. And so I just paid $2 to get $1.41 in performance. Not a good deal. Not a good deal. So you don't want to use longer columns unless you must. But that means longer time to come out, longer time to get your analysis done. So you really like to see short columns, hydrogen, carrier gas, thin films, and so on down the line. We use diameter, phase thickness, phase type. These are what give us our separating power. We can go up actually to 60 meters. I've seen columns 100 meters in length. How's that? Longer than a football field. And you think, oh, that's a pretty long column. But it takes forever to go through that whole football field of length. So it isn't an efficient way to get separation. And there's always this thing in life, and I hate to be a pessimist, but you don't get everything. You get, if you want capacity, put a large amount on the column. It's that you go away from separation ability, you go away from sensitivity, you go away from speed. But you get lots of stuff out. But poor separation, takes forever and so on. If you really want to have speed, you don't get as much sensitivity, you don't get as much capacity or resolution. So what's important to you? If you really tough separation, that may be most important. I need to separate these two compounds. So you pay for it though. So what's important to you? Speed, sensitivity, or resolution. And you make that a cognizant. You think about what is important to me. Because, like I say, this will influence what you buy, what you use, and how long it takes to get your results. Just a real quick comment on troubleshooting. Probably approximately 80% of all trouble in a gas chromatograph is gas flow. We've got gas under pressure. It loves to leak out someplace. If it's leaking out someplace, guess what? You don't get good data. So 80% of the time, if you don't get good data, it's because something's wrong in where your gases are flowing. And I'll point to the places a little bit later. 10% is due to us. We screwed up. So operator, 80% is the machine, 10% is us as operators. 10% is really due to the machine failure. Machines are extremely durable. I have a piece of equipment in my laboratory that's well over 30 years old, and it's as good as anything on the market today in terms of sensitivity, resolution, and that thing still runs perfectly. So it's a good technique. You try to stay away from these kinds of problems and these kinds of problems. It's so seldom these happen anymore. We could probably reduce it below that 10% today. Probably closer to 1% of the time it's the machine. The rest of the time there's a leak someplace or we screw up. How do we monitor this? Control samples. We use two types of control samples. Our first type of control sample is we'll be making injections. Typically we have a machine making the injections for us automatically. We slip in known standards, known concentration. And so the machine's running on knowns, it runs one that you made up, you know what it is. And if it isn't right, the machine's screwed up. There's a problem someplace. So you just randomly put them in your analyses to make sure the machine is running properly. If you're interested in something that's broader, like a quality control, or method control, I should say, then you put a pure compound in at the beginning of your analysis, where you do your extractions, you do your isolation, you do your concentration, and end up having something to put into a gas chromatograph. So you have two types of standards. One looks for the machine screwing up, the other looks for an error in the method. Well, this just talks about where the problems are about maintenance. We'll skip that. Here's the place where we typically have our problems in terms of gas not going the right place. Okay, this is responsible for 80% of our errors. Where do we get leaks? Where can we get problems? Right up there. That's rubber septum. people don't necessarily look after that. We're poking holes through it all the time. And guess what? At some point it's going to leak. This is all under pressure. And so that's the first place we look. There's also a rubber O-ring up here, the seal up here. I've taken this apart sometimes and found this thing's almost dust. People just don't pay attention to the inside. You need to make a seal between this steel body and this glass tube. Again, a nice O-ring here. We've got to make a connection between this long little column and all the gas that's flowing down here. Another place for leakages to occur. Sometimes this valve here that controls the flow through the injection port ends up being messed up. And so there's, again, lots of opportunities. Purge line plugging, valve sticking on the end. And so you always start that way. You start looking for leaks. Where are they? Typically, they're one of those rubber seals. They're seldom on this end. Normally, they're up there or up here. Sometimes here. GC applications, they always involve, or I should say almost always involve, some type of sample preparation. If I'm interested in looking at apple flavor, I can't take the apple and stuff it inside my instrument. It's a little bit of a problem with that. So I got to do something to get what I want away from that apple, separated from the apple. The only place where I really do little or no separation is if I'm interested in kind of what we call the headspace, the area around a sample. And we do this in gas chromatography. We may be interested in milk. This milk stinks. There's a problem with the milk. I can put that milk into a bottle. I can seal it up. I allow it to kind of come to equilibrium. All the aromas come into the headspace in the bottle. I can just take a syringe, go down to that bottle, it's sealed on top, go through the rubber septum, and draw some of the air and take that air and put it into my gas chromatograph. That's how you look for some off flavors sometimes, or quality assurance of foods. But that's the only technique that really you don't have to do any sample preparation. And well, I call it no sample preparation. Put it in a bottle, allow it to come to equilibrium. All the rest of them, we are doing some kind of extraction, some kind of isolation procedure first. Have you all completed the GC, the fatty acids at this point? Oh, 2 more groups to go. Okay. So some of you know the sample process you went through to look at fatty acid composition, right? You couldn't just inject the fat. You couldn't just inject the food. You had to first isolate the fat and then treat that fat to give it something to measure, to give the machine something to measure, and that's the fatty acids. And so we always have some kind of a process that we have to go through before you can put samples in the machine. As I said, we can do headspace. It's called static headspace. It's an equilibrium. There's no motion, no airflow, nothing. Just close it in a container, allow it to come to equilibrium, sample it, and do your analysis. So you can actually directly sample. But we can do some extraction too, some concentration. These are a couple techniques that you'll see. This is solid phase micro extraction. So solid phase micro extraction. The twister is similar, and I'll show you the examples here. These 2 materials love to absorb compounds. They just love to absorb compounds. You put them anywhere near almost anything, they'll absorb it. And so what they'll do is they'll move out of the sample, out of the gas, wherever, and they'll move into one of these 2 devices. Then you stick those devices in the injection port, so it's really hot, and it tends to evaporate them. They evaporate into this stream, and you do your analysis. So we've got some absorbents here. They can be used in gas sampling. They can be used in liquid sampling as well. So they're fairly common. People like these methodologies because they're simple. They aren't always the best, and that's one thing we find today, is people often choose time and money over good data. 2 very, very popular techniques. Say, there is no technique that's good for everything. And people like this because it's simple and misused or overused. The idea of dynamic headspace, in this case, we're taking a food, We could take our rotten milk again, or off-flavored milk, and we could actually start bubbling nitrogen or bubbling helium through that. And then the gas that comes off is going to extract some of those flavors. So the gas that comes off when we bubble through a food product, and we take that gas with its aroma compounds, and we put a little trap on the end, a little granular material, pass that gas to a granular material that absorbs this odor, these off-flavor compounds. That absorbent is called 10X. So that's the material. It again loves to absorb compounds. So again, we can have a static system, we can have airflow system, we can do liquid separation with a syringe, we can do all kinds of different techniques. And there isn't actually a standard method. You just look at your problem and you look at what you want to know. And between them, you come up with some type of a technique. This is the SPME, solid phase microextraction. You will see that. Cindy has this down in the laboratory. Looks like really an awkward kind of syringe. How's that? But as you push the plunger down, the absorbent comes out the end of the needle. And so your absorbent gets put, you can put it above your sample. This then is free out here to absorb aroma. When you've let it absorb your compounds as long as you want, you pull the syringe back up, the plunger back up, pull it out, and put it into a gas chromatograph. And the heat of the gas chromatograph, the heat of the injection port, frees your compounds. This is actually where you've got a little bitty stir bar. And believe me, it is a little bitty stir bar, like a magnetic stir bar. But instead of just being a stir bar, it has a coating on it. A coating that, again, loves to absorb compounds. Doesn't like water a lot, but it likes almost anything else. And so when you put this into a food product and stir for a while, it tends to collect your organic compounds. And so it'll actually collect them on here. Then you take this out, rinse it out, and put it in your hot injection port. Your injection port then flushes anything that was absorbed onto this into your instrument. So each of these, like I say, have some advantages. They have some application. Thing you caution you about is if you look at literature and you find out that, gee, somebody used a certain method for a certain analysis, you still got to question it. You got to think, what did they do and why did they do it? It's really easy to fall in the trap of saying, oh, somebody else used this and it worked for them. Well, maybe it did, maybe it didn't work for them. Maybe it was the best for them, maybe it's the best for you. So you really have to critically examine what you're doing and why you're doing it. Literature is a good place to start. So I'll give you 3 examples in our bit of time. Aroma research, flavor research is my bag, my area of expertise. So you'll find 2 of the 3 examples being related to flavors in one way or another. Actually, only 1 of 3, darn it. Anyway, I'm trying to be fair how to other disciplines. Okay, so in terms of flavor, so what we find is one of our more interesting flavor compounds is the delta-lactones, delta-decalactone. If you smell delta-decalactone, every one of you would say, man, it's a beautiful coconut, absolutely coconut-like. The problem is there's not much of it in coconut. And if somebody wants to make coconut-flavored liqueurs, coconut-flavored macaroons, that sounds a good choice, doesn't it? Coconut flavor, whatever, where do you get this compound? There's not enough coconut to go around. And so the industry works and say, how do we make this chemical that we can use it as a flavoring material? And more we're finding, of course, microorganisms. We're doing fermentations to produce these organisms. And so a particular microorganism, this organism, when grown on the right substrates under the right conditions, produces a significant amount of this delta-decalactone. And so basically we want to analyze this lactone, what this organism produced. How do we know it's pure? How do we know it's a compound we want? Well, this is kind of the process, culture medium. So you're going to culture the organism. You grow it, and you allow it to produce its odor. You know, if you've worked in a microbiology laboratory and ever done anything with plates, many times those plates smell. They have a lot of odor to them. Some are pleasant, some can be meaty, some can be potatoes. It always amazes me the diversity. Well, we want a specific one to give us this particular flavor. So culture medium, we extract with diethyl ether, so we put our culture medium into an extraction. In the laboratory, we just do a separatory funnel, shake it back and forth with ether. The lactone is going to like that ether much more than it's going to like the culture broth. It doesn't like water. It wants to go into an organic phase. So we go ahead and get our lactone moving into the ether. We collect the ether fraction, concentrate, do a little fractionation on a liquid chromatography column, a silica gel, so we just get the lactone fraction out of everything came out, and do gas chromatography. Now, you'll find in flavors that the same compound can have different character depending upon its chiral isomer. Is it a D? Is it an L? Is it an R? Is it an S? What chiral form is it? Some chiral forms have no flavor. A different chiral form of that same compound can have immense flavor. So I can't just look for that lactone. I got to know which isomer of that lactone is present. And so this is an example where looking at delta decalactone, and you'll find the R and the S being separated very nicely here. Primarily the R form of the lactone we want. We validated that there's none of this other one, so this is our isomer. This is the one we want. Here are some other lactones that are just included in this isolation. So chiral separations are not easy. It's tough to separate a chiral isomer, and yet gas chromatography does that fairly nicely for us. In the next one, this is looking at apples. Diphenylamine is used to treat apples prior to storage to control apple scald. So the apples are dipped in 1 gram per kilogram of diphenylamine solution. So pick the apples, dump them in this solution of diphenylamine. We're rather interested in the residue at the time we eat it. Why do you wash your apples before you eat them? This is a good reason. So we need to quantify it. We need to do quality assurance or quality control, whatever we want to call it, to make sure there's a limited amount of this diphenylamine residue on the apple. And so it's a fairly simple methodology. In this case, it's on the surface. It isn't throughout the apple. It's just on the surface of the apple. So I don't have to grind the apple and do all kinds of strange things. I basically can take that apple, wash the surface with a solvent, for example, hexane, take that, pick the apple out of the hexane and concentrate the hexane. So I can concentrate it, and then I can do gas chromatography, mass spectrometry, to validate it's there, and I'm sure it's there because of my mass spectrum. When we do that, that's what's on the surface of your apple, by the way. Let's see, we have roughly 60 compounds, and that's not counting the little ones in between. So we probably have somewhere around 100 different chemicals you find on the surface of the apple. So the question is, okay, now which one of those is diphenylamine, and is it only diphenylamine if I do see a little peak for it? And so that's where mass spectrometry comes in. If we do a mass spectrometry of this pure compound, they say it breaks into pieces, the mass spectrometer blows it into bits. The mass spectrometer counts those bits and tabulates them. And so we find mass 365 out here is really, that's that whole diphenylamine compound. It went through the mass spectrometer, just got counted. But here's a piece of it at 272, blew off some parts of it. Here's some here, some here. This is 169 peak. This is called a base peak. It's the largest peak. And so what we can do is we can tell the mass spectrometer, look, here's our gas chromatogram. We're feeding it into the mass spectrometer. Tell me when you see a compound as mass 169 fragment. If there's a 169 fragment, I know I'm going to be measuring this diphenylamine. So we key our mass spectrometer to look for only compounds that have that mass. And this is an example of it. So here's our diphenylamine standard. Here's where we wash, well, this is an apple extract. So yeah, it's an extract of the apple surface, and here's a blank. So the mass spectrometer limited to all those other 60 compounds. And it says, here's where it is. This is where my standard, that's where my standard runs. Here's where it comes from the apple surface. This is how much it is. We know how much we put in to get this. It's proportionally less. So again, a nice simple technique to be sure of this. So you're actually just doing fatty acid analysis. That's again another technique that's used very broadly for, or I should say, in-gas chromatography. The first thing, well, you didn't isolate the fat in this case. I think that was just given to you. You're looking at pure oils, weren't you? Yeah. So you don't have to worry about isolating it, but if you were going to be looking at what is the fat in a food, you'd have to first isolate the fat, and that might be a Soxhlet or some other methodology. First, you isolate the fat, so you get what I say pure, and I put pure in quotation marks. What is pure? Is 5 parts per million? Does that make it not pure? But anyway, let's say we get pure fat. What you did, or you're going to do, is you take boron trifluoride, and about 3 mils of that, two drops of fat. Put 2 drops of fat into your boron trifluoride solvent mixture. You cap it. You put the tube in a boiling water bath for 1 hour. Add 3 mils of distilled water, 10 mils of hexane, shake well. What the boron trifluoride does is it splits the fatty acids off of your triglyceride. So it takes the fatty acids away, and it makes a derivative of them, makes an ester of them. So if there's butyric acid in your lipid portion, it splits up butyric acid off and makes methylborate. So it's basically, it's taking your acids off, making them free, and it's putting them in a form that's easy to measure, easy to separate. And these things love to be in the hexane. They want no part of that water, so they move into the hexane, and you can directly inject them into a gas chromatograph. It's really pretty simple methodology. I don't know that, or Cindy, I think, is one who looks after this for you. I don't know that she ran any milk fat. Those of you that have done it, was there a milk fat sample? No? Okay. Because what's unique about milk fat in fatty acid composition, fat composition? Anybody remember that? Okay, I'll give you the answer. It has short-chain fatty acids. Short-chain fatty acids. Milk fat is very unique, then contains butyric acid, caproic acid, caprylic acid, C4, C6, and C8. Short-chain acids. And so they're very, very unique to, or in the fat area. And so if you were going to be running milk fat for your sample, you would have a standard run that looks something like this. Cindy would have you run standards. I want to run butyric acid, the methyl ester butyric acid. I want to run it in my gas chromatograph. My butyric acid comes off here. Then when I run my real sample, I look here. Is there anything here? There's nothing here. There's no butyric acid. So that's 4 carbon. This is the 6 carbon, 8 carbon, 10, 12, 14, 16, and here's our 18. So butyric, caproic, caprylic, capric, myristic, palmitic, steric, and then this group up here. So you would run these as all standards so that you've got times over here. There's times at the top. And if you see something there when you run, that's one of your fatty acids in your sample. So you do those simply to find where your fatty acids elute in your chromatographic run. So you'll find the table is there, and so what you really pay attention to, you pay attention to times. So you say, okay, my peak at 1.769 minutes is butyric acid. And you look at area, because area tells you the relative amount of that compound. Time tells you, is it, or what compound is it, which fatty acid is it. Area tells you how much of that is present in your sample. Your samples are going to look much more like this. They're going to be mostly plant origin. Plant origin, we don't find any short-chain fatty acids. You find a little bit of 14 carbon, myristic acid. You find a little bit of, well, quite a bit of palmitic. But you really be out to your stearic, oleic, linoleic, and linolenic acids. So you can be looking here. So in your samples, you probably won't see much at all until you get out into this region. This is blown up a little bit so that you can better see. These are our standards, so I kind of extended that. It's a little bit blurry. I'm not sure it's much of a help. How's that? But you would find your peaks larger. You could tell which one's stearic and so on. And then this is one of the food products. And so you've got, again, stearic, oleic, linoleic acid. So you go back and forth. Here's your pure standards. Here's your unknowns. By time, you can tell what fatty acids are present. And so C16 is the 18 with one double bond, 18 with two double bonds. And again, you tell that from time over here. The same compound will always come out of that column at the same time, again and again and again, if you don't change any of your operating parameters. So your time is your key for what you've got. And then, again, you work with your area percent. The machine can be set up so to do calculations for you. And so this is an example where the machine has been set up. And so it eliminated everything else, and it simply calculated the percent of the total peak area that each peak represents. So this is your C14, not C14. Less than 1% of your fatty acids were C14. Here's C16, 25.5% of your fatty acids were C16 and so on. So the machine can set up, you'll probably do the math yourself, I would expect. But again, fairly easy working with the areas. Add them up and divide each peak by that total area. So that's that. If you have any questions, happy to respond to them. Anything about gas chromatography you ever wanted to know and didn't yet? I think you got out 2 minutes early, unless the instructor wants to get a lecture in.
No.